Hi everyone, I'm Sundar from UCL, and I'll be presenting our work on what do you want from theory alone, experimenting with tight auditing of differentially private synthetic data generation. This is joint work with Georgi and Emiliano, my advisor. Oh, it doesn't work, never mind. So firstly, what is synthetic data? In synthetic data, we want to take an original sensitive data set and we fit a generative model on top of the data set and then sample some fresh records from the generative model to produce the synthetic data set. This synthetic data set is meant to mimic the raw data set both structurally and statistically so that it can then be released to data analysts who can analyze the statistical properties of the original data set without incurring the information leakage from the original data set. However, prior work by Stadler et al. Has shown that in some settings, the synthetic data set can still leak sensitive information about the original data set. This is where differential privacy comes in. Differential privacy is a standard framework for achieving privacy. We assume in differential privacy that there are two neighboring data sets, one with the record of Alice and one without. And the algorithm is run on both of these data sets to generate different outputs. And the idea of differential privacy is that if the algorithm can be shown to satisfy DP, then the outputs with and without Alice are going to be very similar to each other. And therefore, an adversary cannot really tell whether Alice was part of the data set or not. So the standard way of adding DP to synthetic data is in the model fitting process. And basically what happens is that there's noise that is added during the model fitting, which makes sure that the generative model that's trained based on the data set satisfies DP. There's this nice theorem of DP called the post-processing theorem, which means that when we sample a synthetic data set from this generative model, then that gets the DP guarantees from the generative model itself. What we are ultimately saying at the end of the day is that an adversary with access to either the generative model or the synthetic data set or both of them will not be able to infer sensitive information about the original data set up to this privacy parameter epsilon. This epsilon is something like the security parameter that appears in crypto, like 128-bit security and stuff like that. But in this case, it's for privacy, and the lower the privacy parameter, the more privacy you have. So that's like an inverse relationship with privacy. Cool. In the context of synthetic data, there have been many different algorithms that satisfy DP. We focused on three main DP synthetic data algorithms in our work. The first is PrivBase, the second one is MST, and the last one is DPWGAN. And all of these three algorithms have appeared in this 2018 Differential Privacy Synthetic Data Challenge competition, which was run by NIST 5-6 years ago now. So that's also very popular. The reason why we chose them is because they're also very popular and they have been re-implemented by both open source libraries and companies such as Microsoft. So a lot of people are using these algorithms and implementations in practice. The primary question that we are interested in studying in our paper is whether these implementations actually satisfy these DP guarantees in practice. And the reason why we are interested in this is because there's been many prior work that has looked at different implementation of DP-SDG, or even the last one is on in the Gaussian mechanism, and they have identified implementation bugs that are present in the implementations that then mean that they don't actually satisfy any of the DP guarantees in practice. One example is the first one that you see from GitHub. This was reported to I believe this is the one from DeepMind, if I'm not wrong, where they were reusing the random number generator to generate the noise, which means that an adversary will be able to predict all of the noise and basically reverse engineer the whole thing. And this is why we want to make sure that these differentially private synthetic data algorithms actually satisfy DP in practice. The main way we go about doing this is through the process of auditing. And what we do in auditing is we verify that the empirical privacy leakage, basically we come up with an empirical epsilon value, which we then check whether this matches the upper bounds that's guaranteed by DP, which is the epsilon, the privacy parameter. So we want to see whether these things are close together. When the empirical epsilon exceeds the theoretical one, we identify privacy violations, and this means that there are implementation bugs present in the implementation. So the it's not satisfying as much privacy as it needs to. On the other hand, if the empirical epsilon is about the same as the theoretical one, then we can conclude that the audit is tight and that there's no implementation bugs that we need to worry about in the algorithm. Another interesting observation outcome that we can have in the process of auditing is where the empirical epsilon is much smaller than the theoretical one. In this case, the interpretation is that the audit is loose or that the attack that we're using to audit is not good in actually extracting the privacy leakage. And this generally means that the audit is not effective and it cannot find privacy violations in practice and therefore needs to be improved. So in more detail, in the process of auditing, we first choose 2 neighboring data sets. We run the differential private synthetic data algorithm repeatedly, and we run a membership inference attack on the outputs. Then from the attack, we get a false positive, false negative rate, which can then be converted back to an empirical epsilon estimate. And this is done many times in prior work already, the step 4 specifically. In the context of synthetic data, what previously was already done is using black box membership inference attacks that only has access to the synthetic data set. But as I explained earlier, many times the generative model itself satisfies DP guarantees, so we can also consider white box attacks that have access to this generative model directly. There were 2 main prior black box attacks that I used in practice to estimate the privacy leakage. One of it is the distance to closest record metric, which is basically built on this intuition that if the synthetic data overfits on the original data, then the synthetic records are going to be close to the original records. There's also more recent attacks that have been developed by Jose et al., which is based on the shadow modeling intuition, where they extract features from the synthetic data and train a meta classifier on top of this. However, we find that in prior work that's estimating the privacy leakage from synthetic data, they usually use weak black box attacks and also only consider average case neighboring data sets. So they don't consider worst case, what's the worst possible situation of neighboring data sets there are, and therefore they result in loose audits, as I've explained earlier. The empirical privacy leakage estimates are much smaller than the theoretical ones. This means that the privacy audits that have been done in the past are ineffective in actually finding bugs and privacy violations in practice. In our work, we are the first to conduct a large-scale audit of differentially private synthetic data algorithms and implementations. To that end, we actually developed the first strong white box attacks against priv-based and MST specifically. They didn't used to be white box attacks against these algorithms. And also, we craft implementation-specific worst-case data sets in order to achieve the tight audits. So point 2 and 3, we find through our work are necessary to conduct a tight audit of differentially private synthetic data. Our main findings is firstly that black box attacks in general, and especially this distance to closest record metric, which is often used to empirically evaluate the privacy of synthetic data, is completely ineffective in exploiting any kind of privacy leakage, even in this strong DP setting. The second point I just made that white box attacks and neighboring data sets are necessary to achieve tight audits. And we conducted an audit of 6 implementations, 5 of them have bugs. 1 of them was even submitted to the NIST DP Synthetic Data Challenge competition. Okay, so first what we looked at was on comparing the different kinds of black box attacks on their effectiveness on privacy auditing. And what we find is that, so this graph basically shows the empirical epsilon, so those are the bars, and the red lines are the theoretical epsilons. The key thing here is that the bars are not supposed to exceed the red lines, but as you can see in about 4 out of the 6 implementations, it's already exceeding, and that's a big problem. When we looked at the code, they were actually from the metadata violation, where the synthetic data tends to read the ranges or the different kind of inputs for each attribute directly from the data set. This should, in theory, be supplied separately, but this causes a DP violation. The second thing that we find is that of the violations that were identified by query-based, DCR missed half of them. And was still the AUC of the DCR attack in these settings was close to random, whereas as you can see for like MST smart noise, the orange bar, which is the query-based attack, is like completely off the chart. So clearly it's not actually picking up any like privacy leakage in practice. Lastly, we find that the NIST implementations which do not have this metadata violation the black box auditing is not tight. We also fix the violations for the other algorithms and find that in the black box setting, the auditing is not tight. The empirical epsilon is not close to the theoretical one. So we were motivated to look at different kinds of worst-case data sets. You can look at our paper to see the kinds that we played with. Here I'm depicting 1, 2, 3, 4, 5 different kinds that we were experimenting with. And we find that the worst-case data set can be implementation dependent. So this is still black box, but we played with different worst-case data sets, and we find that for specific implementations, specific worst-case data sets work better than others. We also find more DP violations in one specific library due to random seed reuse as well. And lastly, we find that even in the worst case data set setting, DP auditing is not tight when you only use black box attacks. We then move on to white box attacks, and so now we put like the white box attack together with the worst case data sets, and we find that both priv-based and MST can be tightly audited, or is close to tight in all 4 epsilons that we tried. DPWGAN is still not tight, and in order to fix that, we used an active white box attack from Nazar et al. And in this case, we find that the audits are tight. The last thing that I wanted to talk about today is whether our method is any useful in practice, and whether we can actually find bugs. So the first one that we looked at is this bug from priv-based, an old implementation. Through manual analysis, we noted that there's a bug there where the noise scale was calibrated wrongly. And here you can see that our analysis can actually find that it's exactly wrong, how wrong it is. Yeah. Each epsilon is like twice the expected one, and there are some limitations here with our analysis, which we talk about in our paper. The new bug that we found was in the implementation that was submitted to NIST, and here we find that there was an early stopping mechanism where once the privacy budget is hit, the algorithm will stop training, and we were able to trigger it in a very specific circumstance, and this bit was not DP. So that's why you see for very small epsilons of 0.1 and 0.4, the empirical epsilon is actually much larger than the theoretical one. This was an implementation that was submitted to NIST, and so this kind of motivates the necessity to actually automate some of this analysis, because clearly the manual analysis didn't pick up on this. In conclusion, there are some limitations of our work, the computational cost, and the power of our adversary. You can read it. I would like to say that we didn't attack any live systems, so we have an ethical disclosure statement in the paper, and also of the violations that we reported to the library authors, only priv-based Hazy fixed the bug. Thank you very much.